Hi everyone. This lesson is about more of the Bernoulli distributions, but we're taking a slightly different slant, and let's start with this example here. So we have a netball player who knows from experience that her success at shooting goals is 0.65, and we want to know the chances of her taking exactly 4 attempts to get her first goal. So let's start by defining x equals scoring a goal, the probability of success 0.65, and not scoring a goal, missing, is the failing of outcome, so that's probability 0.35. Now we want to know 4 attempts. So really what we're talking about is the probability of, let's see, what is it, missing, so failing, and then success. So missing, then get the goal on the 4th go. So that would be 0.35 multiplied by 0.35, multiplied by 0.35. Try that again. Multiplied by 0.65. Now when I checked that, I found that to be 0.0279, or about a 2.8% chance. Now that stands to reason, because if a person is a 65% accurate shot, the chance of them missing 3 in a row before they get one is going to be a very, very low chance, but it could happen. Now, this example is just one of a more general class of these types of problems where we're talking about these Bernoulli events, but we want to know how many times we'll have to repeat the experiment before success occurs. So let's define a new type of event, and this will be a generic event, and it will be a Bernoulli distribution of x failures followed by a success. So let's take an example here. Let's imagine that I'm new at some sort of a game. I'm new at playing darts, and my chance of throwing a dart and hitting a bullseye is 0.1. Actually, that's probably too high if I'm a beginner, but anyway, that'll do. So my success is, and my failing therefore is 0.9. There's a lot greater chance that I'll miss the bullseye. Now, I'm not so much interested in a single attempt. I'm interested in this new event about how many failures I need before I get a success. So x could equal 0. I might have 0 failures. In other words, the very first throw might be a success. What would be the probability that I was successful on my very first throw? Well, that would just be 0.1. On the other hand, x might equal 1. That means I have 1 failure followed by the success. Remember, x is the number of failures, not the total number of turns. So if I had 1 failure, the chance of that occurring would be 0.9, and then the chance of success 0.1, and so I would get 0.09 as the probability of that outcome. Now perhaps I have 2 misses before I hit the bullseye. So I'd have 0.9 squared by 0.1. I should have had an equals sign there, not a multiplication. And so this would be 0.081. Now I think you can see that I might have 3 misses, 4 misses, 5 misses. This is endless. This goes on forever. And so it's a discrete variable because x is jumping up in whole numbers, but it's an infinite distribution. I could have any number. Now this is, we studied some of these last year. So I would say, here's my distribution. I'll just summarise this. X could be 0. Now what did we find? I'm going to be a bit more general here. X could equal, the probability then would be P if I was successful on the very 0, remember, it doesn't mean 0 turns, it means 0 failures. Success on the first attempt. 1 failure, I'd have Q multiplied by P. 2 failures, I'd have Q squared multiplied by P. Then Q cubed multiplied by P, and so on forever. Now, just to illustrate that, I've made a little bar chart here, which I'll just move over. So that matches the one I'm talking about. So 0 failures, so first attempt, probability 0.1. 1 attempt, there's the 0.09, and so on. And you can see it gets down, and it would keep on going forever. Now you will remember, of course, that the area underneath one of these probability distributions has to equal 1. How on earth are we going to add these things up? So let's find the sum of the probabilities. Well, that would mean adding P plus Q times P plus Q squared times P, and so on. Now I hope you recognise this as a geometric progression. The first term of our geometric progression is P. The common ratio is Q. So that's multiplied by Q, and so forth. And I'm sure you'll remember from grade 11 that the infinite sum of a geometric progression is given by the formula A over 1 minus R. Now, for this to actually converge, the common ratio had to be less than 1, and Q is, of course, less than 1 because Q is a probability, and in our case it was 0.9. So the value of the first term is P, and 1 minus Q, R was Q, but hang on a sec, 1 minus Q equals P, and so we've got that the infinite sum is 1 as required. Now we know from the definition of a probability distribution that all of the probabilities have to add to 1. So this is just a nice little proof that it's a bit hard to spell while you're talking and saying different words, isn't it? So as required, there we go. Now that's just a little proof that this geometric type distribution is a well-defined probability distribution. So that's the first interesting thing. Now let's move on a bit. I would love to know the expected value. So the expected value of this, in other words, on average, the number of turns I have to try before I succeed, the number of failures. So the definition that we had last time, therefore, the sum of x multiplied by probability. Let's just go back to our table for a moment there. So our first value of x is 0 multiplied by p. Well, that's not very interesting, is it? And our next one is 1 multiplied by qp. So that's just q times p. Our next one is 2 multiplied by q squared p. And then 3 multiplied by q cubed p, and so on. That's interesting. Now that's not really going to help much. I'm just going to rub out that 0 term at the front. That's annoying and really not necessary. So here's the trick. We did something like this last year when we were looking at sums of geometric progressions. We'll multiply by q. So this term multiplied by q would be q squared times p. And I'm just going to write that slightly to the side. The second term multiplied by q would become 2q cubed by p. Now I think you can see that this pattern would continue, and every one of the terms above would appear with the same pronumerals below, but with one less as the coefficient. So coefficient 3, coefficient 2, and so on and so on and so on. Now you guessed what we're going to do here. We are going to take the first expression for expected value and subtract the second expression for expected value. So this first one, QP, has no counterpart. There's no term the same, so it would be QP still. This bit, 2 times this minus one of these would be q squared p. 3 of these minus 2 of these would be q cubed by p, and so on. Now that's interesting. I've got a common factor of q outside p plus q times p plus q squared times p, and so on. Now over on this side, I might take a common factor of the expected value outside 1 minus q. So, didn't we see this earlier with p plus q times p and so forth? Let's just go back and see what we saw for that. There it is. The sum of all of those terms, when we worked that out here, that equaled 1. So that's exactly the expression we have in our brackets, p times qp times q squared p. There it is. All of that equals 1. So really, that's just q times 1. The expected value then of this distribution is q over 1 minus q. Now I could express that as 1 minus q is the same as p. Alternately, I could put 1 minus p instead of q over p. So there are 3 different ways to calculate. They're all equivalent, and probably the most common one, and the one that I would remember, is the one there in the middle, q divided by p. That's the expected value. And remember, what was this event? The event was the number of failures before success. So this is sometimes called the waiting time, because it's how many turns you have to try before you succeed. Here's an example. Mike is new to basketball, and he's practicing shooting from the free throw line. He knows his probability of success is 0.2. Let's write that down. P equals 0.2. Therefore, his chance of failing is 0.8. How many times would Mike fail on average? Well, this is just what we're talking about. The expected value, or the waiting time. Q divided by P. 0.8 over 0.2, 4. We would expect him to miss 4 times before he then... Now that doesn't mean he's guaranteed to miss 4 times before he gets the ball in. If we took Mike out to the basketball court and we said, right, start shooting free throws, he might get it in the first time. He might have 2 misses, then we restart the experiment. He might have 2 misses before he gets the basket. He might have 10 misses before he gets a basket. And if we tallied up all of these numbers, in the long run, they would average 4. That's what we mean by the expected value. It doesn't make a prediction of any particular outcome of the experiment. Here's another example. What's the chances that the probability of a random blood donation being type A is 0.4? And we're interested in the number of blood samples that a technician must check before a type A sample is detected. This is the same scenario. So the chance of success is 0.4. Q would be 0.6. Now we want to know the probability that Y equals 6. Now that's not the same question. That's not an expected value. They're giving us a number this time. So the probability that Y equals exactly 6, that means there must be 5 failures before the success occurs. So Y is the number of samples the technician checks until the blood type is detected. Yeah, the wording of the question is a little tiny different to the definition there, so be very careful as you read these. And that came to 0.031, or approximately a 3.1% chance that the technician would find the type A sample on the 6th one. Now again, that's a pretty low number, because a 40% chance of detecting a blood type A, then you'd expect it to occur. You would expect it to occur. The expected value, remember, is Q over P. Q is 0.6, P is 0.4, so that's 1.5. So you'd expect it somewhere, sometimes on the first one, sometimes on the second, but you'd expect it a lot sooner than 6 times. So that's why this is such a low chance. But be careful on the distinction between these two questions. Now, part B, considering this lesson is becoming quite a bit longer than I expected, I might leave part B for you to consider yourself. All right, that's enough for now.